Hi, my name is Amir.
Hi, my name is Dora.
This is our presentation for physics behind flight and application of Bernoulli's principle in airplanes.
The explanation of the lift force still remains controversial today. NASA uses Euler equations to model and explain the lift of an airfoil using the conservation of mass, momentum, and energy. Based on the conservation of mass, the same amount of air particles travel from a wide region to a squeezed region due to the curvature of the upper wing, so they have to move faster. The Bernoulli principle demonstrating the conservation of energy shows a higher velocity corresponds to a lower pressure. We assume that the fluid flow is horizontal and neglect the height difference. Point 2 has a smaller velocity and a higher pressure, meaning the force downwards on the bottom of the wing is greater than the force upwards, generating the lift. We can also notice that the upper airflow tends to follow the curvature of the airfoil. This is known as the Coanda effect. Here, I will demonstrate a simple water model of Coanda effect. Although typically we associate it with air or gas, fluid does share some similar behaviors. The air around the upper trailing edge and the bottom side of the wing will acquire an overall downward momentum due to the motion of the wing. As a result, the wing will also be pushed back up based on the Newton's third law. In conclusion, pressure distribution and the Newton's third law are complementary to provide a comprehensive explanation of lift.
So you might have this question that why airplane cannot fly too high. So as we explained before, lift force is caused by Bernoulli's principle and Newton's third law. But if you look at Bernoulli's principle equation, you see like density is a big part of it. So if you have low density, the difference between pressure below and above the wing is not going to be high enough to have enough force for the lift. And if you look at Newton's third law, we use the air resistance formula for this one. You don't have to know it, but as you can see, this one also have the density, and low density is not going to give us enough force for lift. And another reason is there's low oxygen levels at higher altitude, so the combustion engines of airplanes would not operate properly. So here's an example I made myself. We can quickly practice a little bit of Bernoulli's principle. So this airplane is moving at 720 kilometers per hour. I can quickly convert it to 200 meters per second. Feel free to pause it. I have to go through it quickly. So then it says altitude 14,000 meters. We don't care. We only care about the density of air, which is going to be equal to 0.8 kilogram per meters cubed. And then I'm going to have point A above wing and point B below wing. And it says the velocity above wing is 10% faster, so VA is going to be equal to 1.1 V of B. And VB is in fact equal to the V of airplane. So if you write the Bernoulli's principle, you can say we're going to get this one. If you rearrange that one, we get this other equation. And because of this relation here, I can replace this with 0.21 VB squared. And we have numbers for everything. The height here is going to be just this 1 meter, the thickness of the wing. And we have G, we have rho of air, and we have like a velocity, everything. And we plug everything into this other equation that gives us the force. And the surface area here is going to be the 2 by 10 wings. We have 2 of them, so it's going to be 40 meters squared, and this thing here, it's going to be here. And if you calculate that, actually, we're going to get this answer. Try to actually get it yourself. It's a fun practice. So thanks for watching. Here are resources, and we hope you actually learned something.
Thanks to NASA and Professor Mike Merrifield for inspiring us to improve our explanation and complete this video.